Imagine unboxing a brand new stick of Corsair Vengeance memory. The matte black aluminum heat spreader looks familiar, clean, and understated. The specifications printed on the side appear entirely unextraordinary for a modern mid to high tier build. DDR5 architecture, 6,000 megatransfers per second, low operating latency, and out-of-the-box support for both Intel XMP and AMD Expo automatic overclocking profiles. Nothing on the retail packaging, the glossy branding, or the barcode suggests that this specific stick represents a seismic shift within the global semiconductor supply chain. Yet, when an enthusiast plugs that module into a motherboard, boots up their system, and fires up a low-level diagnostic utility like Typhoon Burner to inspect the underlying silicon, an unexpected detail appears in the component field. The physical DRAM die manufacturer is not Samsung. It is not Micron, and it is not SK Hynix. Instead, the software identifies the memory chips as originating from ChangXin Memory Technologies, better known across the technology sector as CXMT. To the average consumer, this detail might seem like trivial supply chain trivia. Companies swap component vendors constantly to balance costs, manage local inventory, or hedge against regional logistics bottlenecks. But dynamic random access memory is not a typical consumer market. For nearly 30 years, modern computing has relied on an extraordinarily tight, nearly impenetrable triopoly. Whether you were assembling a custom gaming desktop, buying an enterprise workstation, purchasing a fleet of office laptops, or deploying thousands of rack servers in a hyperscale cloud data center, the underlying physical memory dies were overwhelmingly guaranteed to originate from the exact same three titans: Samsung, SK Hynix, and Micron. Together, they control around 93 to 95% of the global supply. Now, Chinese-fabricated DDR5 memory has crossed the threshold into mainstream consumer retail under one of the most recognizable and respected enthusiast brand names in Western personal computing. This development does not imply that China has single-handedly conquered the memory market overnight. It does not mean CXMT currently yields superior silicon, offers lower baseline prices, or builds more reliable dies than its Korean or American rivals. But it highlights a far more subtle and structurally disruptive reality. The high entry door to global memory production has finally swung open, and the market leverage held by the incumbent Big Three is beginning to shift. In hardware enthusiast circles, processors and graphics cards command the vast majority of the attention. Tech forums debate core counts, analyze architectural improvements, compare clock speeds, and dissect multicolored benchmark charts down to individual frame times. Memory, by contrast, is frequently treated as a secondary commodity, important only when a system lacks enough of it. Yet RAM is the active workspace of the modern computing platform. While the central processing unit functions as the high-speed worker executing calculations, memory serves as the physical workbench. If the workbench is too small, too slow, or constantly clearing space, even the fastest processor on Earth drops to its knees, idling while data trickles in from secondary storage. Modern DRAM operates on a fundamentally simple electronic concept that becomes extraordinarily complex at scale. Data is stored across billions of microscopic cells, each consisting of a single access transistor and a tiny capacitor. The charge held in that capacitor determines whether a bit reads as a logical 1 or 0. Because those charges leak away in fractions of a second, the system must read and refresh every cell thousands of times per second. That continuous electrical refresh cycle is precisely what the dynamic in dynamic random access memory signifies. The physics become terrifying when viewed through the lens of mass manufacturing. A single modern DDR5 die contains tens of billions of these microscopic cell structures packed onto a piece of silicon no larger than a fingernail. A single weak cell, erratic leakage rate, or unstable timing margin can trigger random bit flips, leading to application crashes, blue screens, or silent data corruption. Furthermore, the memory must maintain stable timing characteristics under rapid thermal cycles, ranging from cold boots to prolonged heavy computational workloads inside hot server chassis. Making DRAM is not merely a matter of etching circuits onto silicon. It is akin to constructing an apartment skyscraper, where every room must flick its light switch on and off in flawless synchronization billions of times a second, while the entire building undergoes a continuous earthquake, and selling the result with a multi-year warranty. This sheer technical difficulty explains why the industry consolidated so brutally. Over the past 40 years, dozens of well-funded semiconductor firms across North America, Europe, and Asia attempted to compete in the DRAM arena. The market's aggressive, cyclical nature acted as an economic sieve. When demand surged, profits soared, driving companies to build multi-billion-dollar fabrication facilities. But as new production capacity hit the market simultaneously, supply outstripped demand, triggering severe price crashes. Companies that lacked vast financial reserves, cutting-edge yields, or massive manufacturing scale were wiped out during these down cycles. The survivors, Samsung, SK Hynix, and Micron, emerged stronger after every crash, absorbing intellectual property and expanding their market share until they stood alone as an oligopoly. To understand why this specific Corsair memory module matters, one must examine its technical characteristics and retail positioning. The kit in question is a 16GB Corsair Vengeance DDR5 desktop stick sourced within the Chinese retail market, identified by a part number ending in the suffix CN. Unlike early domestic memory releases in regional markets that relied on lower clock speeds or loose timings to maintain yield stability, this stick operates at mainstream performance specifications. It runs at a data rate of DDR5-6000, primary latency of CL36, an operating voltage of 1.35 volts, and supports both Intel XMP 3.0 and AMD Expo. This is not a low-speed green PCB module intended purely for budget office desktops, nor is it a prototype resting on a laboratory bench under test probes. It is a mass-market retail product designed for gaming PCs and content creation workstations. It is vital to maintain appropriate analytical caution. Corsair has not issued formal corporate press releases highlighting its integration of CXMT dies into its global supply chain. The verification comes from independent hardware analysts, teardowns, and diagnostic profile reads shared by hardware publications. However, the implications remain clear. A top-tier international memory brand with a global reputation to uphold has evaluated, validated, and placed its brand warranty behind silicon manufactured by ChangXin Memory Technologies. Founded in 2016 in Hefei, Anhui, ChangXin Memory Technologies entered the semiconductor landscape at a massive structural disadvantage. While Samsung, Micron, and SK Hynix drew upon decades of cumulative manufacturing experience, proprietary patent portfolios, and fully amortized fabrication facilities, CXMT had to build its technological foundation almost from scratch in a highly restricted international environment. In semiconductor manufacturing, yield is the ultimate metric of survival. When a factory processes a 300mm silicon wafer containing hundreds of individual memory dies, the economic viability of that wafer depends entirely on the percentage of functional, error-free chips harvested. If a fab's yield sits at 30%, the functional chips must absorb the entire manufacturing cost of the ruined silicon, making them wildly uncompetitive. If the yield rises to 85 or 90%, the cost per chip drops dramatically, turning production into a highly profitable enterprise. For its first several years, CXMT focused on mature memory standards like DDR4 and low-power LPDDR4, using these older nodes to train its engineering staff, optimize its chemical deposition steps, and refine its lithography yields. Once those processes stabilized, CXMT skipped rapidly into the DDR5 era, expanding its catalog to include both standard 16-gigabit dies and advanced 24-gigabit dies, rated at speeds up to 8,000 megatransfers per second. The introduction of 24-gigabit die densities is particularly strategic. In memory architecture, 8 bits equal 1 byte. Therefore, 24 gigabits divided by 8 equals 3 gigabytes per die. Placing 8 of these 24 gigabit dies onto a single physical memory stick creates a 24 gigabyte module. Combining 2 of these sticks produces a 48 gigabyte dual-channel kit, while 4 sticks yield 96 gigabytes. For decades, desktop RAM capacities grew in strict binary steps: 8 GB, 16 GB, 32 GB, 64 GB, and 128 GB. But non-binary memory fills the massive financial and technical gaps between those traditional steps. Modern games increasingly exhaust 16 GB setups under high resolutions and heavy ray tracing workloads, yet 32 GB kits sometimes exceed a budget builder's price target. A 24 GB or 48 GB kit offers an ideal middle ground. Running large language models locally on a personal workstation requires vast quantities of system RAM to host model parameters without offloading to slower storage. A 96 GB kit offers massive capacity without forcing the user to pay for enterprise-grade 128 GB or 256 GB ECC configurations. Similarly, video editors working in 4K or 8K timelines often hit memory limits on 32 GB systems, but 48 GB provides the necessary headroom at a lower cost threshold. By offering competitive 24 gigabit dies, CXMT gives module vendors like Corsair, KingBank, and Glowway a way to differentiate their product lineups through flexible kit capacities, rather than competing purely on rock-bottom prices. To understand why a Western company like Corsair would seek out an alternative DRAM supplier in the first place, one must look at the massive structural shifts occurring at the high end of the semiconductor market, specifically the global boom in artificial intelligence infrastructure. AI accelerators depend heavily on high-bandwidth memory, or HBM. Unlike conventional desktop DDR5, which connects to the CPU via traces running through a printed circuit board, HBM stacks multiple physical memory dies vertically on top of one another, using microbumps and through silicon vias. This dense 3D matrix sits on a shared silicon interposer directly adjacent to the main processor logic die. This architecture enables absurd data transfer speeds, delivering terabytes per second of bandwidth required to feed billions of matrix math operations in real time. However, HBM is exceptionally difficult and resource-intensive to manufacture. Producing a gigabyte of high-bandwidth memory requires roughly 3 times the physical wafer capacity and manufacturing resources of a gigabyte of standard DDR5. Furthermore, stacking 8 to 12 physical dies vertically means that if a single die in the stack fails during final packaging, the entire multi-die assembly must be discarded. Because enterprise cloud providers building AI data centers are willing to pay massive premiums for HBM, profit margins far exceed those achievable on standard consumer desktop RAM. As Samsung, SK Hynix, and Micron pivot massive portions of their global wafer allocation toward lucrative HBM contracts, a structural deficit opens in the market for standard, unbuffered DDR5 consumer memory. The traditional memory giants are effectively moving their primary focus toward the high-margin enterprise market. This dynamic creates a prime entry point for an emerging competitor like CXMT. CXMT does not need to instantly outpace SK Hynix in HBM design, nor does it need to win every extreme overclocking world record. It simply needs to manufacture stable, high-yielding, standard DDR5 dies in sufficient volume to satisfy the baseline needs of consumer module brands. In commercial supply chains, the presence of an alternative supplier changes market dynamics long before that supplier captures a majority market share. For nearly 30 years, the DRAM industry operated like a closed room containing a single table with only 3 chairs. If a memory module vendor like Corsair, Kingston, or G.Skill wanted to buy high-volume silicon, they had to accept the pricing, allocation caps, and terms set by the Big Three. If one incumbent experienced fab contamination, another shifted capacity away to server memory, and the third raised contract rates. Module makers had no choice but to absorb the costs and pass them along to PC builders. A credible fourth DRAM manufacturer fundamentally alters these supply dynamics. Even if Corsair only shifts 10 or 15% of its total global memory volume to CXMT dies, The mere existence of that alternative option gives Corsair powerful leverage when negotiating bulk wafer pricing with Samsung or Micron. During global supply disruptions or demand spikes caused by new computing cycles, a fourth manufacturing base helps smooth price spikes, preventing severe retail shortages. Additionally, by supplying domestic Chinese system integrators and regional consumer brands, CXMT frees up global production capacity from Korean and American fabs to serve other international markets. Despite this milestone, ChangXin Memory Technologies faces significant technical, operational, and commercial hurdles before it can truly challenge the incumbent triopoly on equal footing. First, short-term synthetic benchmarks and initial boot stability tell only part of the story. Memory chips must maintain signal integrity across years of thermal stress, continuous electrical refreshes, and varied workload patterns. Server-grade adoption requires even stricter validation standards, where defect rates must remain near zero across hundreds of thousands of continuous operation hours. Second, the semiconductor industry is notoriously cyclical. Surviving a downturn requires massive cash reserves, high yields, and efficient cost structures. CXMT must prove it can weather severe market down cycles without requiring continuous capital infusions. Finally, demonstrating high-speed DDR5 6000 or DDR5 8000 dies in limited batch runs is vastly different from yielding tens of millions of identical, defect-free dies per month at ultra-low production costs. However, commercial adoption inside recognized enthusiast brands creates a self-reinforcing feedback loop. As more CXMT dies reach real-world consumers, engineers gain valuable operational data, process defects are identified and eliminated, revenue grows to fund next-generation fab equipment, and customer trust expands. The history of the semiconductor industry shows that major market shifts rarely happen overnight with a single cinematic breakthrough. Instead, they occur quietly, building up through process refinements, yield improvements, and subtle supply chain integrations. A single Corsair memory stick running CXMT chips at DDR5 6000 speed is not the end of the traditional DRAM order, but it is unmistakable evidence that a new player has stepped onto the board, hidden quietly beneath a simple black heat spreader, performing its job one clock cycle at a time.